Greetings, gentle readers, fellow earthlings. June 28th, 2026. Ross Finlayson here today with Reading Foundations. The previous episodes were from Mancosu and Brouwer and Weyl and Hilbert on the foundations of mathematics in the 20th century. And the previous two episodes before that were reading from Reichenbach on the philosophy and the foundations of quantum mechanics and the idea that the Schroedingerians are kind of like the Lorentzians as for quantum mechanics, for relativity theory. Whatever fulfills solving or embodying those makes models of those. And so then there's room in the theory, that being room in the formalism, and then room in the data for the new physics that's really the old physics that's underserved in a sense in the modern accounts that kind of have arrived at grasping at these partial straws that they've made for themselves that no longer have any content that can really result more than truncations, and the reductionism of the cancellation and the approximation and the truncation and the corrections as they are of the vanishing marginal returns in a sense. So then the mathematics was about, in the context of Brouwer, that almost always introduces intuitionism vis-a-vis constructivism. And here that there's just the superclassical accounts from the classical expositions of the superclassical or Zeno's arguments to what make for the foundations today that's becoming a sort of fragmented pluralism, since there's these giant monsters of mathematical independence since Erdős and the paradoxes of mathematical logic to be resolved, that there's instead this idea that this great atlas of mathematical independence, after three models of continuous domains, three laws of large numbers, three models of arithmetic, three Cantor spaces, three probabilistic limit theorems. The standard linear way only has one, and that's because the other ways that contradict each other according to readily derivable paradoxes. And then for why accounts of motion and so on are given just the one standard way, the usual standard linear curriculum's account of then what's called standard. It's called Euclidean and Archimedean, Cartesian, and as for the piano arithmetic and these sorts of accounts, has it that here there's a greater account, a wider, fuller dialectic, for that towards a constant, consistent, and complete and concrete theory, or this thea theory, that it's sort of beyond the uniqueness of the standard account, and it's walling off, painting away, hiding and ignoring away, otherwise the inconsistencies that would arise from line reals instead of field reals, or signal reals instead of field reals, or laws of large numbers out beyond large numbers to larger and largest numbers, these extraordinary accounts that then made it so that there's a first class emplacement of continuity and infinity instead of discreteness and finitude in the theory, so that the mathematics is equipped for the foundations with the paradox-free reason of the wider, fuller account. And then the physics gets involved with the continuous and replete nature of the continuum and the reticulum for the orbifold after the geodesy for general relativity's account of motion and gravity and the laws of mechanics and physics. And here that there's the unlinear account as well for heft, and the momentum is pseudo-momentum, lost in the wash, making it so that the definition of momentum is kind of curtailed and deconstructed to be reconstructed again. Then for the quantum mechanics, it's a continuous quantum mechanics. So that being just a brief recapitulation of an account of the foundations for logic and mathematics and physics and science. Then I'll just gather the rest of the books from this one box that started quite a while ago that had all these books in quantum mechanics that have been being read out in reading foundations. See if we can get to the bottom of this box, and so that next time that we can get to the next box of books. So what we have here today is a stack of books. And this stack of books is about 10 deep. And on top of this stack of books is a book called Void, The Strange Physics of Nothing, by James Owen Weatherall, author of The Physics of Wall Street. A pleasure to read for the curious reader, and an invaluable source for scientists and philosophers, Carlo Rovelli, author of 7 Brief Lessons of Physics. I'm not a big fan of Carlo Rovelli. He doesn't really tell me much. But he's popular, and the brief accounts and so on are having that there's still I don't really have anything otherwise notable about that. So what this says is the Weatherall talks about nothing. So nothing in vacuum sense is mentioned here. You got the Dirac positronic sea, which is the idea that after quantum mechanics came about, is basically the idea is the only way that there could be like no absolute rest everywhere, is be motion everywhere, is this Dirac positronic sea. And so this is constantly electrons and anti-electrons separating and then colliding again and doing nothing in this vacuum state. And so for the Dirac positronic sea, this basically gives an account of a space, and so it's like a setting for ether and these sorts of accounts, that after a doubly objective relativity theory, there's room in the theory for the ether theory again. And for the Fitzgeraldian and space-contraction always, the length contraction and time dilation together, and correspondingly the relaxation of that. That the Dirac positronic sea is the usual account given to the vacuum physics. And then there's also an account for gravity, and then if that's for the charge, and then for the kinetic, there's the Einsteinian white hole sea everywhere. So this is the same kind of idea as the positron and antipositron, or otherwise the Dirac positronic sea. And the white holes and black holes, one being a singular attractor, the other kind of a singular repeller, that this makes, it's a theoretical particle, the white holes. And then for any kind of black holes, which could be like atoms or galactic nuclei or highly relativistic dynamical systems, according to the usual mathematics after Chandrasekhar and Schwarzschild, of gravitational singularities, that besides the, how one might say, the Dirac's positronic sea, which is held up as existing in physics and quantum mechanics. It's real to the quantum physicists. Then this Einsteinian white holes, to go with black holes, so positrons, antipositrons, black holes, white holes. The account then is in the vacuum that's like they're everywhere, and so it's the sea is just like an ocean of these things, and then that's the account of what kind of nothing is in the vacuum. So then, as with regards to nothing, and then the canon, then there's Aristotle. It's like nature abhors a vacuum; it can't stand a vacuum, an emptiness. Something would fill it in. So this usual idea that there's a continuum, it's an idea that it's a Platonic ideal, from that there's one of the things, and these sorts of accounts. So the emptiness then is a physical account in these. Then the other idea from nothing is after being. So being is a great Platonic ideal, and so it's ancient in Greek, and then the later continental German philosophers, 2,000 years later, reconsidering the same sorts of developments, but after the Renaissance and after the Enlightenment, during the Enlightenment, the rational Enlightenment, came to say, being is this great central concept since Kant, Immanuel Kant. And then that being one of his greatest accounts, it's because he also has the Ding-an-Sich. It's like, well, it's being in itself, the thing on Sich, thing in itself, being, and the thingness that's since like Duns Scotus and Hecate and Quixote and the medieval scholastic doctors of the church, who are the philosophers technically. So then Kant also has the sublime. So these are these two super classical concepts, the Ding-an-Sich and the sublime, that go along otherwise with just classical being. And then after that, you got Hegel, and he steps up with nothing. He's like, well, according to a dialectic, there's complementary duals. So for a being, there's a nothing. For a universal, there's a void. For a space, there's a point. For an account of like the point and the local and the global and the total, these are after these complementary duals, then the meeting in the middle, and then whether we are in the macro scale or the meso-scale or the micro scale, we're in the meso-scale or in the middle. And then the micro scale and the macro scale are these accounts of what it means to exist from our perspectives, the perspective, the projection, and the perspective. So geometry is motion is an account here, and it's meant specifically and rather technically, not just metaphorically or as something, just the profundity of itself, for the actual approfondissement, the attainment of what geometry is, that thusly the concepts of being then nothing get into a great account in the philosophy of as for objects of thought besides objects in reality, vacuum and emptiness. So then later that's picked up by Heidegger as like being and nothing, and he kind of weighs them against each other with regards to existentialism and nihilism. So in the account of the 20th century, first Sartre and after Derrida and the great postmodern philosophers of the 20th century, then there is existentialism, the being and-ness, in the concept and the state of being, and then there's the nihilism, the nothingness. What it means to intend to consider what it means to entertain the ideas of the void, or as with regards to attaining a connection to the universal. That these are the sorts of accounts. So then, as Leibniz put it quite some time before that, it's like, well, the fundamental question of metaphysics. And so if we have a physics, then we have a metaphysics is like the meta theory. It's about the theory. And a meta theory. But here we just have one theory. So the fundamental question of this theory is, why is there something rather than nothing? And the idea is like, well, it's just given in like the usual literary and even liturgical accounts. It's just provided that there's something rather than nothing. And then the other idea is that it's like, well, it wouldn't matter if there was something or nothing because they're either the opposite. And so if one or the other, if you just can't tell, but at the same time, it wouldn't matter because they're complementary duals and they would fulfill making each other like so. So it is provided yet, and it's a fair account. While at the same time, it's also attainable by reason that it wouldn't never be not provided. So that's the idea of being and nothing then. To figure it out, then there's a book about void, the strange physics of nothing. And it's from 2016 or so. The plenum of the void, waves of space itself. Here there's spiral waves and wave spirals. And then the space is the frame spaces and space frames. So the wave spirals and spiral waves is models of change in an open system. So there's the energy is like the content, and then it's like any form of matter and charge or light or otherwise potential for power. There's the energy in the entelechy, the continuum. So here he has like a plenum, the plenum and the void. So that's the space and the emptiness, and the frames and the spaces, and the space and the frames. So then there's the spiral waves and wave spirals as wave mechanics, models of change in an open system. There's frames and spaces for relativity, and it's all entire the usual kind of since the Hamiltonian, and the classical mechanics and the mechanics, and here about the space contraction linear and space contraction rotational. that being distinct, because before it's just ignored, and it is distinct for the ideas of heft and these things, that the energy and the entelechy and the space frames and frame spaces then have the tetrads of quantities, of forces, of quantities in units and the fields so corresponding to them make for the usual sorts of accounts of the formulaic treatment of physics. The nothings. This might speak to another account of what's emptiness or the empty set in something like a set theory. And it's often gets like, well, what's the empty set? It's like, well, a set is defined by its elements. So what's the empty set? Is like, well, a set is defined by having no elements. So it's given as a constant in the usual account of the theory, like Zermelo-Fraenkel set theory. It's just said there exists a set and it's empty. But then matters of vacuity and the trivialities. So when something's trivial, it just kind of arises as like, well, it's just an immediate direct consequence. It goes so much without saying. We just call it trivial. Whereas the trivia is like from the triviandum, just like, you know, the three subjects classically and these kinds of things, the quadrivium and these kinds of things, the four subjects. The trivia is just something that is like a lemma, and mathematically it's so, but it just doesn't really attain to anything else that is kind of like so. So the accounts after the emptiness and the empty set, and there being a constant given in this theory, because otherwise you couldn't really say it exists. But it's just then used in all these trivial accounts of results that it's given as a useful concept that the definition and introduction of the empty set as an axiom in set theory is considered usually introducing a constant, so then it causes expansion of comprehension. Yet, as well, there are ways to look at the empty set that it's according after these matters of mathematical paradox, that is full of stuff. That there's one for each type of thing in the entire universe, its own kind of nothing. This is about usually a relation of apples and oranges. That apples and oranges, you can compare their counts and other accounts about them, but 0 apples equaling 0 oranges, it does not mean that when there's 1 apple that there's anything less than 0 oranges. So having the empty set assigned to both of those has otherwise in any system of types, there's a default, an implicit, a null, a value, empty, for each particular type. So it's similar in programming languages, just null is given as like, it's just the absence of any value at all. But at the same time, an empty type is, or rather an empty value of any given type is its own type. So the axiom of 0, or the axiom of the empty set in set theory, is a restriction of comprehension itself. And so when getting into axiomatics, and that being basically saying, well, we have axioms and they make all the rules and you can't add any more. These are all the axioms. That's it. Has it that an expansion of comprehension leaves that free? It says, well, then everything goes. It is what it is. But a restriction of comprehension is a particularly conscientious act to say, it's like, and this is excluded, that this exception is a rule. Rules otherwise not having exceptions is making a rule of an exception. So this gets into another part of the reason why the matters of the void and the null and the empty are a lot like the infinite and the universal and the sortes or heat paradox and these sorts of accounts as to why there are paradoxes associated with emptiness and so on, mathematically and logically. So besides in the physical account of Aristotle and saying is like it just can't exist because something would fill it in, the tendencies and propensities of all the dunamis and dynamis, the power and potential around it would fill it in with something. There's also the mathematically and logically so why the void and for nihilism and accounts of nihilism has it that because it's got mathematical paradox close to it, not necessarily intrinsic to it, because in these sorts of deconstructive accounts we break it down and put it back together as to how it can be so. has it that then that's why also nihilism is associated sometimes with despair, or with the lassitude, or the accounts of being so disconnected from everything, that the existentialism is being in the world, and the nihilism is all these vacuous, trivial exemptions and exceptions to that. So that said, it's the void is yet also considered a great wellspring of possibility and potential itself. So there are quotes about the void that are both is from a positive aspect and a negative aspect with regards to its character as being conceivable and what its content is. But in a theory where an object in its universal context is defined in all its bodies of all matters of relation by everything that it's not, that there's to solve the Kuhnen inconsistency of higher set theory, there's an elementary embedding of context into the universe itself by being the universe set minus that context. That an apple removed from the universe is everything that it is not. It is yet this sort of reflexive account. That these are again just usual accounts that the void is the universe and the universe is the void. So this is this dual monism and the dually self-infinite consistent, and that's to why then this is the void is a very primary and fundamental concept in theory. And it's usually left out, but then later picked up and then deployed to make like vacuous results like the result material implication or principle of explosion. These other logical accounts that lead to fallacies by providing some cheap expediencies that make possible some ways to just consider something without having to consider all the accounts of wider relation in only considering small closed categories and the like. So are there then to be three laws of nulls, three laws of zero and the empty and the null? Yeah, that seems the usual way to go about it. Kind of like for identity, there's equality, tautology, and identity. And these sorts of laws, and making for different reasons why that, like the tautology is like why things are alike or not different, and equality is like, well, there's an intentionality, which it means that they're absolutely identical in all models of the theory, and then there's extensionality, that there's no different, like one apple and one orange is one of each of those. It's extensionally the same, but intentionally they're different. And then here why like these nulls or the empties of those are extensionally the same, intentionally they're different. These are just usual sorts of accounts then to add for the various paradoxes of the things that, as for example, when infinity is introduced in set theory as considered an expansion comprehension, but it's a restriction because it introduces a constant omega, the inductive set. But at the same time, it's ordinary when by any count of quantification over the elements it would be extraordinary. Similarly, it's so with the empty set. And then looking into it, that it's infinite, or otherwise that it's not a set, and these sorts of accounts. So this is part of this setting where it's given kind of a fuller treatment. Because otherwise, one can just make trivial, obvious accounts using logic and break otherwise these simpler theories. Acknowledgements, notes, bibliography, index. Is it empty? Is it really empty? Why is there something rather than nothing? So this is the fundamental question of metaphysics. There's a very old question, famous or infamous, for its difficulty. Why is there something rather than nothing? Part of what makes the question difficult is not clear what could possibly count as a satisfactory answer. So this reads a lot like Nozick, who basically is a close student of Leibniz, but kind of writes it in his own terms. Newton. He held that space could be thought of as an infinite container into which stuff could be placed or removed without affecting the structure of space itself. See, here there's that's not exactly so. Say if we removed all this stuff in the universe, we'd be left with empty space. Doesn't seem like a substantive physical assumption, much less one that could be false. But this is as wrong as anything as physics could be. Here it's just considered. That's what it is. That it is what it is. Galileo Galilei in Italy and René Descartes in France were no more sympathetic to the ideas of bodies moving through empty space than Aristotle had been. I would have read that that's not so, because Galileo is in the Galilean frame, and René Descartes has an origin in the Euclidean, and those are the spaces that they're working in. So the Weatherall comments on Descartes saying he rejected Aristotelian physics and attempted to replace it with a complete systematic physics of his own. I wouldn't say that. I mean, he attempted to extend it, not replace it. Part of this project involved developing a complete metaphysics with accounts of space and time, God, and matter of all sorts. He was an early advocate of the idea that an adequate philosophy of nature must be based on mathematics. So that's as old as the ancient Greeks, because like the Democritus has atomism, and it ends up being mathematical because it's the formal accounts of the objects of the logic and then the objects of mathematics that make mathematics what it is. In our view, and so then the account here of Aristotle and saying that Descartes wanted to come up with Descartes' account of subtle matter, meaning the various kinds of forces, vis-viva and vis-motrix, vis and theta, that Leibniz and Newton had a great debate about which was which and which was in effect, and what that means for the Galilean who just says equal, opposite, and rest, motion, unstoppable, immovable. It's linear. I'm Galileo. If it spins, don't ask me. I don't say. And these sorts of accounts. Have it that this is the authors. I would suggest making a point that it's not necessarily so, because we follow the canon and there's much to it. For Descartes, the primary property that an object had was its extension, that is, its shape in space. And we'll hear the frame spaces and space frames make for an object is considered to be mostly space. An atom is considered to be mostly entirely space. Its extent or the extension here. And then as for bodies being that, but it's a space frame and a frame space. So it's doubly objective relativity theory, and then that's why then Descartes' account of a body as an extension. Let's see. Its shape in space is that, yes, of course, it has a space that it's in. Space, meanwhile, was nothing but extension, the shape of the body's occupying space. So here he seems to indicate that Descartes already had this kind of context built in, and so I'd be able to rehabilitate that perhaps a bit easier than trying to figure out otherwise this way. Space and stuff in it. Thus Descartes reasoned all of space must be filled with some sort of very fine, unobservable stuff. He called this material the plenum. So here that's like that in modern field theories, after quantum theories, it's the Dirac positronic sea, or corresponding what would be this Einsteinian white hole sea, because Higgs is only a partial account. If you think this idea seems strange or even question-begging, after all, Descartes defines space in such a way that can never be empty, then you're in good company. And so that doesn't say that there isn't yet a space. That in doubly objective relativity theory, there's relativity of motion and relativity of space. So then there's also absolute motion and absolute space, but they work out relative to each other in terms of accounts of the Fitzgeraldian and space contraction, about running constants in these sorts of accounts. Arguably, even today, our best current physical theory is positive plenum, and then for ether theory, you'd have to call that an ether. It's like the space that the electrical fields live in. And for kinetics, it's for Einstein, it's coordinates that according to whatever geometries in the geodesy they live in, the orbifold, that objects orbit each other. Or they don't gravitate in the usual account of the geodesy, just following the world line. You got Newtonian pull gravity, Einsteinian follow gravity. It's Newtonian in the limit. And then you got Fatio and LeSage push gravity, like the outside universe pushes in all the objects and makes gravity, and the objects just kind of naturally resist that to the least degree. Then this fall gravity is that again. So you got pull gravity and follow gravity, and then push gravity and fall gravity here, and that's considered to be like finally there's something that doesn't have at least every single body is constantly making all the force in the universe of gravity. So they're just inert. It's an inertial system. And then as to why that the ultramundane corpuscles, because Leibniz was looking at Fatio and LeSage's theory of gravity back then in the time of Newton. It's an entirely competing system of the world, you know. And said, you know, I can't really make it with these ultramundane corpuscles. Or if it was not Euler or somebody like that, perhaps it was Euler instead of Leibniz. And you'll excuse me if I ever get anything like that wrong, but the ultramundane corpuscles is the account then of what that would mean to have something super classical. It's mathematically infinitesimals. Has real analytical character because it equals inverse square the force of gravity as we can know and measure it in the limit, or vice versa. That makes it instead of it makes that. These are the usual accounts that get into it when you have a theory of everything with space and frames. What Descartes envisioned. Newton penned one of his remarks, talk about Hooke's law and Descartes. Indeed, by the time of writing, Newton and Hooke were serious rivals, disagreeing bitterly over the nature of light. Here there's a theory of light and color, about the dual tristimulus color space, the chromatic and prismatic of color, and then about the light and the pure diffraction, vis-a-vis the compounded refraction. Of electromagnetic waves. The light is different than electromagnetic waves. And again, there's room in the theory, there's room in the formalism, and there's room in the data. So there's room in the theory because it's just claimed they're different. They have that light is chargeless and electromagnetic waves are not chargeless, for examples. And then in the formalism, it's like, well, we model everything by having diffraction. It's like, well, you can model the electromagnetic waves as compounded refraction, but the light waves is actually pure diffraction. That they occur of kind of a continuous manner, whereas the radio waves and what information and signal we have in them is not radio noise, but the radio signals is bouncing in a compounded refraction. And then the account is like, well, the light's image is entirely because it's decoherent. What arrives into our eyeballs and becomes a signal and an image is all the sums of all the decoherent images. But in electromagnetic waves, it's all the sums of coherent images. They're entirely opposite. They're functional effect. So that's also an entirely different theory of light. And then as for Newton and like for particles and waves, and the great idea of photons and this and that since then, is obviously it's known to modern physics that light has the character of being both particle and wave, and then that's applied to all of quantum mechanics. So besides after energy, then there's radiation, and so then the energy is kind of accounts of points in a space, or the energy in an entelechy, the contents of the space, and the radiation is given as wave mechanics almost universally. And so then it's got waves and wave spirals and spiral waves. And then furthermore, different kinds of radiation are quite varied. Heat, light, radionuclear, and all these sorts of accounts. They're different kinds of radiation, just kind of like they're different kinds of energy. And so it's fair to say it's like, well, energy is conserved, and that the propagation of radiation is according to these to make the invariance, the Galilean invariance, and the Lorentzian invariance, a motion of what would be either a particle or the aspects of a wave, that there's room in the theory, room in the formalism, and room in the data, particularly for science, that keep it so that these are various, and it's good. And then he makes an unfortunate pun about Hooke's stature. Hooke was a dwarf, or a midget, say. I don't know the various kinds of chondroplastic dwarfs or achondroplastic or these sorts, who by either genetic carriage or mutation are just particularly short. So if Hooke was particularly short in stature, then when Newton said, if I saw so far, it was from standing on the shoulders of the giants. That was really kind of a pretty snide comment. People today might kind of lionize that and say it's like, it was there, the mountain. We climbed it. It was there. But another reading here is, and Weatherall is kind of laughing at the joke, is not funny. Leibniz. Newton and Leibniz. And this kind of thing. So, and then talking about the plenum. And then, so we talked a little bit about what's going on with the emptiness and the void in physics, the void in logic, and the void in philosophy. Why it's a reasonable thing. Speed of light and the invariance theory. Here the speed of light is it's free of metered radiation in space, and then space contraction is what makes it in effect. And then there's Fresnel lensing and the occult Fresnel, which helps explain why when light enters rotating frames, that dark matter is explained by rotating frames being independent, and dark energy is explained instead of tired light as by that it actually goes around several times to arrive at where it's done. Explaining things like the orientation of the moon in the sky and various sorts of effects that are visible and demonstrable in classical sorts of the experiments of the sky survey, besides just very, very reasonably in everyday accounts. Feynman and quantum electrodynamics and quantum chromodynamics, bibliography. Well, I mentioned Krauss's book because this came out, it says 2012, and it's like, why is there something rather than nothing in physics? And it's been read here before, or looked at, and it doesn't really arrive at much, but it helps entertain some of the issues, and it's not unentertaining. David Albert, 2012, criticized the sense in which nothing is used in Krauss's book, pointing out that nothing as understood in modern physics is strikingly different from nothing as understood pre-theoretically. This review led to a heated exchange, mostly on the internet, with a number of prominent physicists and philosophers weighing in on everything from what Krauss had accomplished to whether the philosophy has any value. Well, these days I think we know that philosophers are getting a lot more credit than what they were, because as physicists, philosophers can break any otherwise poorly designed scientific theory, whereas otherwise it would just be computed. Let's see then, this next book is Wavelets, a concise guide. Amir Humayun Najmi, Wavelets, a concise guide. Najmi completed the mathematical tree posts at Cambridge University and obtained his DPhil at Oxford at Johns Hopkins University's Applied Physics Laboratory, and is a faculty member of the Whitting School of Engineering CE programs in Applied Physics and Electrical Engineering from Johns Hopkins Press. So the wavelets here are considered with regards to otherwise accounts of transforms. And the mother of all wavelets is like, there are multiple accounts of what makes the mother of all wavelets. There are various different accounts. So a wavelet is like an infinitesimal change. It's like, well, what is it that makes like a wavelet begin at all? And then how can we make like a whole matrix of those? And then how does it make it so waves kind of live on that? There's transforms in theory after the Fourier-style analysis and Fourier transforms and this kind of thing. The wavelet transforms have their own sort of account, and then about like radial basis functions and wavelets vis-a-vis the exponent and the sinusoidal and the Fourier-style analysis. That this is a great book on wavelets, and I'd look to read it some more. So it's analysis in vector and function spaces, has it. That's chapter 1. Chapter 2 is linear time invariant systems. Chapter 3 is time, frequency, and scale localizing transforms. Chapter 4 is the Haar and Shannon wavelets. So Haar almost usually introduces after the convolutive setting, the Haar measure and then the Haar transform and these kinds of things. That's considered a great enabling result is the Haar and the deconvolutive, particularly the aspects of it. Just like the Hermitian is good for anything or the adjoint is good for anything, the convolutive and deconvolutive settings are good. General properties of scaling and wavelet functions. Discrete wavelet transform of discrete time signals. Wavelet regularity in Dobitschis or Dobitschis solutions. Zero moments of the mother wavelet. Well, there may be others. These sorts of accounts. Orthogonal wavelet packets. Wavelet transform in 2 dimensions. I looked to this later, and about when these arrive at making for like they have non-standard functions to make their derivations to stand them up as formalized, so that then chips can be implemented in them and use them for all such matters of like the graphical compression of picture elements of this video or any sort of account where wavelets are employed. After something like the cosine transform is used, for example, JPEG and MPEG, and the wavelet transform is used for JPEG 2000 and the like. These kinds of things. That's something I'll look to a little bit later. So this next book is Selected Papers on New Techniques for Energy Conversion, Thermoelectric Methods, Thermionic, Photovoltaic, and Electrochemical Effects, Fusion. Edited by Summer and Levine. 37 papers by Joffe Telkes Harold, Herring, Douglas, Jomont, Post, Austin, Wilson, Fahn, Rappaport, Morehouse, Domenicali, Moss, Bowers, Harmon, and others. Over the last few years, world's technologists have made significant strides toward the solution of an incredibly difficult problem, converting a given energy source directly into electrical energy. Oh, this has got a bunch of it's got a bunch of great papers on like, well, here's just like different battery cells, for example. Proceedings of the IRE, Lalande cells. The Lalande cell consists of a zinc anode, a caustic soda electrolyte, and a cupric oxide cathode contained in a glass jar. So like the Leyden jar. This is the Lalande cell. Stimulated by World War II, the development of reserve batteries has involved the study of various electrochemical systems and procedures for activating the cells of batteries. So there can be many different technologies of power cells and batteries and the conversion of these kinds of things. Current voltage characteristics of the NP alloy junctions, and that's the indium phosphate that's used in many technologies of power conversion. Cadmium tellurium. In general, the technology of cadmium tellurium is behind that of gallium arsenide and indium phosphate. Is that? And the use of this material is hampered by the lack of low resistivity crystals. So these are usually accounts of the substrate and the matrix and the crystals and the doping, or like it's kind of like when you have a grid or a matrix, and so then within that grid or matrix, then you can fit elements within the grid or matrix. So the doping of the crystal is just saying, it's like, well, we got like a crystal of silicon. Well, we're going to put these particular elements within, and they fit within the crystal, so they'll be held in the crystal, and then the electricity, they'll behave as vibrators and oscillators at the quantum mechanical level. And as to why then these sorts of accounts of charge, and these devices and these systems are of accounts that would be like as for a supercapacitor and these sorts of things. A solid state quantum mechanical supercapacitor. Heat to electricity by thermionic emissions. Molybdenum cathodes. Apparatus for measuring thermal conductivity. So this is something like from the Physical Review, 1954. This is a collection of papers, but it would make sense to go to the primary sources. Let's see here. This next book is called Earthmasters: The Dawn of the Age of Climate Engineering by Clive Hamilton. A dazzling and multi-layered exploration of the strange and terrifying world of geoengineering. Trees, soil, and algae, the solar filter, coping with the problem, Promethean dreams, compared with carbon dioxide removal, justifying geo-research, the terrestrial biosphere, many bibliographic references. This is something to read, as it has a lot of context with regards to current events and these sorts of things. Electroweak interactions. Now, this we looked at before, an introduction to the physics of quarks and leptons. Renton. So I'll look at that a little bit later. The direction of time. So this is Hans Reichenbach again. So we're reading from Reichenbach the philosophical foundations of quantum mechanics. It says the direction of time. So the direction of time here is always forward. The time dilation, as it's usually put, never makes for an account of negative time. It always is still going forward. So clocks slow, or they meet. And so then the account of rotational setting is like, for example, when something goes around a number of times, each time it meets. But when it's distant away and as it returns back around, and there's never a case where one of the other clocks will have gone backwards. There are accounts of like gravitational singularities as being particularly contrived examples. It's like, well, could something go in and then the clocks just stop and then it would stay there forever? It's like, yeah, that's not an unusual account. But would it actually go backwards, or would there be closed time-like curves? The usual answer would be no, because then causality would be violated. And that was a big account from Reichenbach in the philosophical foundations of quantum mechanics, was that causality is inviolable. And so then that's a totally usual thing in all such matters, since science has never falsified that time irreversibility. Time has never been proven to go backwards, is the point. Then let's not speak about things like entropy and growth and these sorts of accounts. It still goes forward, the time. And then the account in relation to causality then has the key statement and framing is there are no closed time-like curves. So there's a space-like, the light-like, and the time-like. And the idea is that the whole idea of the light cone is like nothing ever goes back in time. And so then everything that's kept invariant about that, and the whole Lagrangian, a system parameterized by time, is according to T, the universal parameter time for a universal clock hypothesis. So then is time a dimension? It's often said that, well, the fourth dimension is time, and that's a great way to look at it. You can just plot a dimension, but you can only kind of plot a semi-dimension and see it as a ray of time. Then about time is change, and it was time just natural. It's a universal clock hypothesis, just kind of given. It's kind of like, well, space goes on forever and time goes back forever. So there's three dimensions of space on one hologram, and then a ray of time, or the silver thread of time. And then they're just kind of either side of a dual that makes for why there's the space-like and the time-like for space and time. So when the discussion was starting, it was like, well, is the void space? And it's like, well, did time stop, or how's it go? That the account here is that just like the infinitive in language is interrupted by making it so that a verb is given its tense and these sorts of things. That the ray of time for causality is a proviso, given a universal clock hypothesis. So then about the statement that there are no closed time-like curves, another way to refine that and make room in the theory is there are no closed finite time-like curves. So the infinitesimal time-like curve that's closed is the account of chance itself. And it gives room for the space-time to expand and contract as all these things move about and around in all the frame spaces and space frames. So there are no closed time-like curves is that there are no closed finite time-like curves. The idea that there are closed infinitesimal time-like curves is just like the Zolfrey metric. That's what it equips. It says we're going to take the Euclidean smooth plane. It's geometrical. It is a plane. It is a flat, perfectly flat plane. It's smooth. And they have Poincaré's rough plane. It's like it's Euclid's plane, except also everywhere there's a point on it. It's rough. And then the idea is like also for the Zolfrey metric is like, well, the metric is 1.0, and then the Zolfrey metric is also that every single point is a circle or a sphere, or otherwise that it's a closed infinitesimal time-like curve. So this leaves all the invariants and such great, and lets everything flow in the doubly objective relativity theory, where motion is relative, space is relative, time is absolute. So I'll look to that in a minute. What that might well be. See, this is a book from the social setting. Marcus Harrison Green's Readying to Rise. Introduction by Sonia Green Ayers. These are the decades of a nation wrestling with whether to reach for the best of itself, a man bearing his soul, and a journalist coming to terms with his calling. Tyrone Beeson, journalist, Los Angeles Times. So this is mostly about it's a book in social justice theory, and as I looked through it before, it's an account of the issues going on with social justice and all this kind of thing. It's said to be social justice isn't ideal; it's not a reality, and it's from Seattle. Volta Press, Seattle, Washington. And it describes matters of ethnicity and race. Talk about after the coronavirus. So this was written after the coronavirus and the many events involved in the early 2020s in Seattle, which is a very multicultural place. Let's see. F. Ziegel, Zigel, Wonders of the Night Sky. So this was published by Mir Publishers, so it's from the Soviets. 1964, revised from the Russian Institute, revised from the Russian, printed in the USSR, about the constellations, the sky survey, a general survey of the night sky. The circumpolar constellations, constellations of the seasonal skies, the night sky of the Antarctic, the Milky Way, and the zodiac. So, relating the Earth to the sun, the Earth revolves around the sun, and then the sun kind of tracks the pole star, and so usually that's pointing at Polaris, or has for about 15,000 years. But 15,000 years ago, it pointed somewhere else. It drifts over time. And so one of the ideas of like, well, how does light speed have exactly what it has is 3.00 times 10 to the 8 meter per second. So like the idea is kind of like, well, it's this from that, and it's twice the speed that the Earth is making with the sun about the moment arm of the pole star. So the night sky of Antarctica, well, that would probably just talk about the auroras, as after the magnetopause and the magnetosphere about the Earth, and the interactions of the ionosphere with plasma from the sun, making the auroras, then it just talks about this. So here we read star lore, and star lore is a great account of like where do the constellations come from in their names, and it's like they come from prehistory. I mean, they're around since before the floods and all this kind of stuff. So that's just usual. John H. Spencer's PhDs, according to Sir Roger Penrose, enormously refreshing. The eternal law, ancient Greek philosophy, modern physics, and ultimate reality. A powerful integration of science, philosophy, and spirituality. Its roots are ancient, while its unique interdisciplinary vision is foundational to the new emerging consciousness. Is there an eternal mathematical law underpinning all of physical reality? Yeah, why not? How does it depend on higher metaphysical ideas such as beauty, symmetry, simplicity, and unity? Symmetry, usually. The dually consistency, usually enough. Is truth objective? Oh, yes, quite. Why were many of the key founders of modern science inevitably drawn to ancient Greek philosophy? It's the one we have, and it's the one everybody already studied, and it's the one we know, and it's pretty good. It's pretty thorough. And so the accounts then, the medieval philosophers had to pick up and clean up and put together and pick a course. Because the medieval philosophers have they basically do the same arguments as the ancient philosophers again, but they also have all the surrounds of how their arguments developed. And so that's like the whole setting of the great debates, and gives us the hundreds of years after the Augustinian, which here is considered the beginning of the scholastic movement. And then after the Muslim Enlightenment and Renaissance kind of put together Avicenna and Ibn Averroes and these sorts, great figures. Then there's Aquinas and Duns Scotus and Occam. And so Aquinas is like, I am an Aristotelian and pretty thorough. And Occam is like, I'm a nominalist fictionalist, but I read Aristotle, and that's what we're going to use. And we have a bunch of stuff to figure out, so let's just leave it at that. And then Duns Scotus is like, these are ideals. This is infinite. This is real. And this is infinity, heicity, and quiddity. And these are all part of these are the sublime. So then hundreds and hundreds and hundreds of years after that, or about 300 or 500 years after that, then after the Renaissance and Enlightenment in Europe, then like Kant is like, we all studied the same classics. And now this is how we're putting our super classical kind of back into it, while at the same time detaching and just saying that's all very rational. If you need to have it that way, I don't necessarily, but you can, and I can perfectly well maintain and defend my arguments that way too. Viva voce Kant, Immanuel Kant. And then Hegel is a bit more or less like, and we definitely have the ideal as the ideal, that Husserl and Derrida later have to say, yeah, geometry is real, geometry is true. Can't be just saying that everything is abstract and theoretical. So yeah, I'm kind of against Wittgenstein and against Heidegger, and Nietzsche, and these being the kind of the anti-Platos that I put forward. Nietzsche is more chaotic. I consider him more of a classical figure. Is Nietzsche. Copenhagenist, so he's talking about quantum mechanics. Einstein in the Anti-Physical Manifesto quotes Bohr and Fine, Einstein quoted and Fine, Heisenberg, Schrödinger, Hilgevord, 2006. Talk about logical systems. Furthermore, if geometry is like arithmetic, then there's a likeness between them, which is to speak of an analogy, which is part of logic. There's three kinds of identity. Gibbons, Einstein, Heisenberg. here we read D'Espagnat, Physics and Philosophy. Here we have definitely. I'm not finding anything yet that the author here, Spencer, says, except he just said the idea of having constant, unchanging relations with varying terms is a fundamental aspect of Platonism. I don't know about varying terms because the terms are true as well. Cervantes also notes that for Proclus, and that would be Euclid's proofs, and so for proof theory, and in Platonism generally, truth is a relation, not a thing. Well, it's always modeled as a thing. It's what is and is not so. Which at first glance makes Platonism sound like structural realism. I think that the author's kind of approaching this from various different angles, and so it's kind of difficult to approach something from various angles. That's one thing. Then this last book in the box is Time, Light, and the Dice of Creation, Through Paradox in Physics to a New Order, Philip Frances, Franses. This I'll try to pick this up a little bit before the next episode and get into it. Paradox of Time, Quantum Time, Gödel's Quality Beyond Logic, The World, Orientation, Joining, Advanced Quantum Theory, and here my dog ear was at this page talking about Wheeler and Feynman. Oh, and the advanced and retarded, the accounts of those being multipole moments and quadrupole moments and so on and beyond the standard account that Wheeler and Feynman get into why those are outside Feynman's usual theory. Well then, gentle readers, thanks for watching today. Good day. So this started with the emptiness and ended with time, but it's kind of a physical account. And so then thusly it's about philosophy and physics, and there is one, and then it's Platonistic, amicus Plato. Amicus Plato.